this video, we're going to be discussing Taylor polynomials and their applications. So first, we just want to give the definition of a Taylor polynomial, with the idea being that a Taylor polynomial is the first n terms of a Taylor series of a function f centered at a. So the nth Taylor order polynomial for f at a is that Tn of x is equal to f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a times x minus a cubed over 3 factorial, all the way up to whatever our nth value is going to be, the nth derivative at a times x minus a to the n all over n factorial. Okay, and so the key application in working with Taylor polynomials is that they're going to be useful for approximating functions. So before we get into some more details, let's remind ourselves what Taylor polynomial approximation of functions is all about. So remember this applet that we've looked at a few times. Here I have my sine function, and I'm trying to approximate the sine function using some Taylor polynomials at some point here that I have negative 0.7 in there. Notice that as I add additional terms here from the linear approximation, I've got cubic, then 4th degree here, I'm getting a better approximation to the sine function. So what I have showing here is now the 8th order Taylor polynomial, and as I would add more and more terms, I'd be getting a better and better approximation. So this is the sort of picture that we have in mind when we're thinking about Taylor polynomials. I have that sine function, and then I have some long certain order Taylor polynomial that I'm using to approximate that function. Let's just look at a couple other examples here. Here I have maybe my arctangent function. I could start with a linear approximation here and then increase the number of terms I want to use in my Taylor polynomial and get a better approximation to that function. Okay, so this is the idea that we have in mind for using Taylor polynomials to approximate functions. So the next piece that we want to think about is not only how we can find those Taylor polynomials, and that's something that we will look at, but for those Taylor polynomials to be useful, we want to be able to say how good an approximation the Taylor polynomial is to the function for particular values of x. So to estimate the error in the approximation, we'll be using either Taylor's inequality or the alternating series estimation theorem. So to use the alternating series estimation theorem, we'll have to have an alternating series that our Taylor polynomial is based on, but otherwise we can always use Taylor's inequality. So just to remind ourselves what these two estimation theorems say, Taylor's inequality says that if we can get a bound on the n plus 1th derivative, if the absolute value of f of n plus 1 in an interval around our center is less than or equal to some number m, then the bound on the remainder will be less than or equal to m times x minus a to the n plus 1 all over n plus 1 factorial. And our alternating series estimation theorem says that the absolute value of our remainder is less than or equal to that magnitude of the n plus 1th term. Okay, so we'll have an opportunity to use both of these estimation theorems in some of our examples. So let's look at our first example here. I have the function f of x equals the square root of x, and I want to approximate f of x by the second order Taylor polynomial centered at 4. Okay, so that means I want to find t2 of x for this particular function. Okay, so note that the second order Taylor polynomial would be f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial. Okay, where here I have a is 4, so I need to figure out what f prime and f double prime are at 4 to be able to complete my formula for the second order Taylor polynomial in this case. So it can be useful to organize the information that you have to find in a table. So I'm going to need to find my nth derivatives, and then I'm going to need to find the value of those derivatives at my point a equals 4. Okay, so I only need to go up to the second derivative. So I only need my n values here to go up to 2. I know that when n is 0, that's my original function, so this is actually root x. When n is 1, I'm looking for the derivative of root x, so we know that that's 1/2 x to the negative 1/2. Okay, and then our second derivative will be negative 1/4 x to the negative 1/2 minus 1, or to the negative 3/2. If we plug in 4 into these, notice that I'll have the value of 2 when I do square root of 4. My value at the first derivative will be 1 over 2 root x, or 1 over 2 root 4. Okay, so I'll get 1/4 for my value at the first derivative, and for my value f double prime of 4 here, I'll have negative 1 over 4 times 4 to the 3/2. We know the 3/2 root of 4 would be the square root of 4, which is 2, cubed is 8, so this is going to be negative 1 over 4 times 8, or negative 1 over 32. So this gives us that t2 of x is equal to 2 plus my derivative, first derivative at 4, which is 1/4, times x minus 4, plus I'll have negative 1 over 32, which is my second derivative at 4, times x minus 4 squared, and I need to remember to divide that by the 2 factorial. So if I wanted to simplify this a little bit, I have 2 plus 1/4 x minus 4 plus negative 1 over 32 divided by that 2 factorial. So 2 factorial is 2, so this is negative 1 over 64 times x minus 4 squared. Okay, so this is our second order Taylor polynomial, and then here we have a graph illustrating the second order Taylor polynomial approximating our function. So the red function here is y equals root x, and the blue function here is t2 of x. So we can see that near 4, we have a pretty good approximation of this blue function to the red function. But we want to be able to say numerically how good an approximation that second order Taylor polynomial is to our function when x is in a particular interval. So let's say x is between 4 and 4.2. So we're looking at near the center here. I want to say how good is the approximation if I wanted to find, the square root of 4.1 using this Taylor polynomial. How close would that be to the actual value of, say, the square root of 4.1 or something that's in that interval between 4 and 4.2? Okay. So what are we going to use to estimate the accuracy here? Well, we don't have a strictly alternating series, so we are going to use Taylor's inequality. To help us answer this question. Okay, so that means I'm trying to get a bound on R2 of x. So I'm using the second order Taylor polynomial, so I need a bound on R2 of x. So that would be less than or equal to some m times x minus 4 cubed, okay, to the n plus 1 over n plus 1 factorial. Okay, if we can find a bound on our n plus 1th derivative. So let's see. Here n is 2, so n plus 1 is 3. So we're trying to find a bound on the third derivative, okay, to help us find a bound on our error. So what is the third derivative in this case? Well, here we have f of x is root x. So we know that f prime of x, which we found earlier, is 1/2 x to the negative 1/2. Our second derivative was negative 1/4 x to the negative 3/2. So our third derivative is 3/8 x to the negative 5/2. Okay, so we're trying to get a bound on this derivative when x is in this interval between 4 and 4.2. Okay, so here's where we're going to do a little bit of inequality manipulation to help us find a good choice for m. So if 4 is less than or equal to x is less than or equal to 4.2, I can try to manipulate this inequality here to get a clear bound on my 3 over 8x to the 5 halves. So we want to know, what is 3 over 8x to the 5 halves bounded by when x is in this interval? So if I take these values here, I want it to look like this 8x to the 5 halves. I could multiply everything, or excuse me, take each piece of this inequality and raise it to the 5 halves. So I could have 4 to the 5 halves is less than or equal to x to the 5 halves is less than or equal to 4.2 to the 5 halves. We can multiply each piece here by 8. So I have 8 times 4 to the 5 halves, 8 times x to the 5 halves, 8 times 4.2 to the 5 halves. So notice that's preserving everything in my inequality. Now, what I want is for that 8x to the 5 halves to be in the denominator. So if I look at the reciprocal of each of these pieces, notice that that's going to change the direction of those inequality signs. Okay, and then the actual thing that I'm looking at has 3 over this 8x to the 5 halves. So I could multiply each piece here by 3. Okay, so notice that that gives me the derivative that I'm interested in getting a bound on, and shows that that derivative is in fact less than or equal to this 3 over 8 times 4 to the 5 halves power. Okay, so this manipulation here gave me the m that I'm going to need. Okay, so since for x between 4 and 4.2, that's our interval around the center, our third derivative in absolute value here, 3 over 8 x to the 5 halves, is less than or equal to 3 over 8 times 4 to the 5 halves. Okay, and we can go ahead and simplify that if we want, figure out what that number is equal to here. I'm going to have 4 to the 5 halves, that's going to be 2 to the 5th, so that's 32 times 8. We end up with 3 over 256, and I can use that for my m value. Okay, so we're spilling over here a little bit onto the next page. But notice that this means that, so our remainder here, our error, is going to be less than or equal to this 3 over 256 times x minus 4 cubed over 3 factorial. Okay. Again, remember that since we have this x is between 4 and 4.2, I now want to get a bound on x minus 4. Notice that x minus 4 has to be less than or equal to 4.2 minus 4. So that's less than or equal to 0.2. Okay, so we can say that our bound here, less than or equal to 3 over 256 times 0.2 cubed. Okay, if x is less than 4.2, x minus 4 is less than 0.2, so x minus 4 cubed is less than 0.2 cubed. And this is all over 3 factorial, or 6. Okay, so if I didn't have a calculator, I could just say this is my error bound, but if I would like to know a little bit more about what that equals using a calculator, I realize that this is 0.0000, we got 4 zeros here, 156 is our error bound. So depending on what you may want to be using this approximation for, that may be a good enough approximation to just use the second order Taylor polynomial to approximate your square root function. If you wanted an even smaller error, you might need to use a higher order Taylor polynomial.